Now that we have seen what a full Smith chart with both impedance and admittance charts overlaid on them, let us see how it is useful for designing impedance matching circuits that typically consists of either capacitive or inductors, capacitors and inductors connected either in series or in shunt that can transform a given load impedance to some other point in the Smith chart, to some other impedance that is essentially some other point in the Smith chart. If we want to match that particular load impedance to the characteristic impedance Z0, we would want that particular point to move to the center of the Smith chart. So let us see that now that we have in an impedance matching circuit at least two components, which is inductor and a capacitor, which can be connected in two different ways, either as in series or in parallel. Let us see how by connecting them, there are four different possibilities, how each possibility moves this particular point in the Smith chart. So in essence, we are having an inductor that can be connected in series to a load, or a capacitor that can be connected in series to a load, or an inductor that can be connected in parallel to a load, or a capacitor that can be connected in parallel to a load. So first, let's look at series connection, and there are two possibilities, either a series L or a series C. Since we are looking at series connection, what we should be looking at is the impedance chart. We have to not look at the admittance chart in the Smith chart, identify that particular load impedance in the first place in the impedance chart, and by connecting either an inductor or a capacitor, this particular point is going to move only in the impedance chart. We need to observe its movement only in the impedance chart for series connection. Now, we know that an inductor has a reactance, so does a capacitor has a reactance. Both of them don't have any resistance. That means either due to an inductor or a capacitor, the movement in the Smith chart is going to be along the constant resistance curve. Is going to be along the constant resistance curve, which is this particular curve that we see here. Let us take first, how does an inductor connected in series move in the Smith chart? We have a certain load impedance. When we connect an inductor in series, all we are essentially doing is this impedance plus this impedance is going to be the looking in impedance at this point, and that is going to be given by this expression where we can clearly see that the reactance is going to be increasing. So the reactance is increasing. And in the Smith chart, how does that move? We can see that when the reactance of this particular load impedance is increasing, we are moving in the clockwise direction along the impedance chart. We are moving along the clockwise direction. So a series L moves this point in the clockwise direction. How about for the capacitor case? When a capacitor is connected in series, we know that the reactance of a capacitor is negative, is minus j over omega c, is minus j over omega c. So when you connect a capacitor in series, essentially the reactance is decreasing. A decreasing reactance in the Smith chart means that we are moving to the capacitive region, which is down below, and that means we are moving still along the constant resistance curve, because none of these two can offer a resistor. They just offer a reactance which can be either increasing for an inductor or decreasing for a capacitor. And since the reactance is decreasing for a capacitor, we are going in the counterclockwise direction down in the Smith chart. We are going in the counterclockwise direction. So that is for a series C. So how about the other two possibilities when we connect the inductor and the capacitor in a shunt configuration? That means in parallel. Since we are looking at a parallel connection, since admittances add up in parallel, we look at the admittance chart to monitor the movement of that particular load impedance. So let's take a look at an inductor when it is connected in parallel to a particular load. The load impedance is ZL, so its corresponding admittance is going to be YL. But when we connect this inductor in parallel, we know that the inductor has a positive reactance, but in terms of admittance, it is negative. It is minus j over omega L. Since it's minus, there is a decrease in the susceptance. So we need to go back to the admittance chart in the Smith chart, the Y chart in the Smith chart, to locate how that particular load is transforming. We know that the upper half of the admittance chart is negative susceptance. Since the susceptance is decreasing in the admittance chart, the movement by connecting a shunt L is going to be in the counterclockwise direction towards the upper half of the region where the susceptance is negative. So a shunt L is a counterclockwise direction in the Smith chart, in the admittance chart to be more precise. How about when we have a capacitor in parallel? We know that the impedance of a capacitor is 1 over j omega L, so its admittance is going to be j omega L, and it is a positive number. So that means by connecting a capacitor in parallel with a load impedance, the susceptance is increasing. And we know that in the admittance chart, since we are connecting the capacitor in parallel, we have to look into the admittance chart, and positive susceptance is in the lower half. This particular impedance point is going to be moving in the clockwise direction, reaching the positive susceptance region. So in essence, when you're having four different possible configurations of connecting either an inductor or a capacitor to a particular load impedance, the movement in the Smith chart is going to be in four different ways. When you have a series connection, we look into the impedance chart, and when we have a parallel or a shunt connection, we look into the admittance chart. And the movement for an inductor in series is going to be in the clockwise direction, and it is going to be in the counterclockwise direction for a series C. For a shunt L, it is going to be in the counterclockwise in the admittance chart, and for a shunt C, it is going to be in the clockwise direction in the admittance chart. All these four movements are going to be either in the constant resistance curve for the series case and along the constant conductance curve for the shunt case. So by tracking the movement of this load impedance, we can transform any particular load impedance to any other point in the Smith chart through using proper L and C values either in the series or shunt combination, which is what impedance matching is all about. Designing an impedance matching circuit is all about.